Good morning, everyone. Welcome to One Concept, Multiple Tools, Multiple Learnings video series. And this is your video number 12. And the focus of this video is totally on momentum, impulse, and usage of momentum and impulse. Okay, so I found out some of the interesting videos, YouTube videos, and as well as simulations corresponding to this topic. So in fact, two more topics which are left behind is collisions and as well as conservation of momentum and conservation of energy, which I'm not dealing it over here, though the concept is very much related to this, because here itself I have a number of resources and take some time, nearly an hour, I think, to complete this. As a result of it, I'm doing it for the next video. Okay, anyway, without wasting your time, let me just share my screen and show you. Okay, to begin with, let me start with the first series, not on simulation, but on a video. So today what we are going to do is we are going to watch a movie, not complete movie, part of it, which is nothing but Spider-Man, Spider-Man 2. Okay, let me begin with this. So this is a scene that we observe in Spider-Man. The URL is here. A small part of it, someone has already clipped and put it over here. I'm not just doing it myself. And then what I do is, let me make it full. So here at the last scene, at the end scene, Andrew Garfield and Emma Stone have been stuck, and the villain, that is I think his name is some Goblin, Green Goblin. Yeah, I remember this. We had this in our comics also. So what he does was, there's a fight between these two, and finally Spider-Man is stuck in a system of gates, and then he's been released, and so suddenly Emma Stone, not Emma Watson, Emma Stone, the heroine, okay, comes Gwen, she loses the control from there, and she falls from the top of the building. The building's height could be somewhere around 300 feet. If you convert it into meters, it comes out to be around roughly around 91 meters. So I consider that. And as a result of it, when she falls down, Spider-Man tries to hold her with the help of the webbing that he puts it across using his what you call his hands. Okay, and this is what is the scene. And finally, he is unable to save her. Okay, and she dies. And now let us see that movie, that part of it, that scene. So what actually happens? So what actually happens is when she stops from there. Let me stop this share. Yeah, when she falls from there from a greater height. Initially, her initial velocity was zero. I'll do one thing. I'll share it my screen once again through a PPT. Let me show you a calculation as how this has been useful for analysis of physics. Now, it is like this. This is the top of the building. This is the top of the building, and from here, Gwen falls from here, his heroine, and then she falls here, and this is the place just before she hits the ground. The Spider-Man, he actually takes this one, a web link, and then he puts a web and he captures it. Okay, this is what happens over here. Now, let us say the mass of Gwen was seen to be around 50 kgs, very slim. And as I said to you, that let us say this is around 90 meters tall. So as a result of it, the velocity when she reaches here, before touching the ground, she doesn't touch the ground. Before touching the ground itself, he holds her. That's what has been seen. Velocity would now be equal to v square is equal to 2gh, because it's free fall. So I can now say v is equal to root of 2gh, which should be square root of 2 into 9.8 multiplied by h is how much? 90 meters. 90 meters. When I do this value, let me take my calculator and see what is the value I get. I get this as 2 into 9.8 multiplied by 90, which will be 1764. And when I take the square root of this, comes out to be around 42 meters. So the speed of her is seen to be 42 meters. Okay. So if this is 42 meters, the mass of it is seen to be 50. So therefore the momentum when she is at this point is equal to 50 multiplied by 42, which should now be equal to 50 multiplied by 42, which will be 2100. 2100 Newton second, or maybe I can say kg meter per second. And when you take this 2100 Newton second, okay, now what happens is, let us say the web link that comes over here, it comes here and it catches over here. Let us say time for which this Gwen is in contact with the web link is seen to be webbing is seen to be, let us say for example, she is in contact for half a second. If she is in contact for half a second, then the time taken or the force that acts on her, because it's a sudden force that, okay, that pulls her upwards, right? Okay, even though this goes over here, okay, it goes and catches over here, and the moment it hits over here, it just holds over here, there's a jerk being seen. Okay, and therefore the force of the jerk is seen to be F multiplied by delta t should be equal to change in this momentum. F into delta t. What is delta t? Delta t, let us say, it takes half a second, should be equal to change in momentum. What is change in momentum? Change in momentum, the initial momentum when she is about to touch the floor is seen to be 42 meter per second, 42 meter per second, 42 kg meter per second, kg meter per second. Sorry, not 42. So this is your velocity. This is your velocity, and this is your momentum. The momentum is 2100 minus, when the webbing comes and keeps her into contact and makes her to come rest, then the final velocity is seen to be 0, or final momentum is also seen to be 0. It will be 0 divided by time taken is half. Maybe you should take 0 minus 2100. I should have taken it the other way around. Anyway, we just take the magnitude of this. Wait. This is a change in momentum, delta P. Okay. As a result of this, the force, the force that acted on the string, or maybe you can say that acted on her spine, right? So this is the Gwen over here, and the webbing actually came over here, and this is the spine over here, this is the neck over here, this is the neck over here. So therefore, the force that acted here should now be equal to 2100 divided by half, which should be equal to 4200 Newton. 4200 Newton. 4200 Newton, which should now be equal to 420 times G. Taking G value equal to 10. Here also I should have taken 9.8 I have taken, but anyway, I'll take this as 10 over here, 420 G. So it is like you're pulling upwards with the force of 420 G, and then the same force is acting on the neck here, which means what? The neck is being pushed downwards with the force of 420 G. 420 kg of weight is dropped on your neck. As a result of it, what happens? The neck snaps off, right? So as a result of it, Gwen did not die of a shock, but instead Gwen died because of the extra large force that was acting on it, right? So how nicely, okay, one can say this is what happened. In fact, this was first time published in 1973 in the Spider-Man comics. And when Spider-Man 2 was released as a movie, then in one of the journals, I don't remember what was the name of journals, I think it is Wizard magazine. There was a controversial series which was asked, saying that, okay, so is it that Gwen died because of the shock, or is it that Gwen died because of the webbing that hit her, okay, that tried to hold her here? Actually, Spider-Man did not have an intent to kill her. Spider-Man wanted to save her. But what actually happened was, okay, you're so stupid that he did not understand the exact physics behind it. And he thought, okay, anyway, I have power. I'm going to do this. And this is what resulted into it. Gravity doesn't listen to anyone. Whether you are a Spider-Man or a Superman, the nature of physics always rules, right? So this is what happened. And this is how finally we can conclude, saying that the momentum was so high, so the force, okay, which ensued because of the change in momentum, which resulted for a very short interval of time, okay, was very, very high. And this, in fact, killed Gwen. So thus, it is not the force that is actually important. It is the force at what time does it act. Okay, the momentum, the change in momentum that we encounter creates an impact. That's why whenever we talk about a momentum, there's one more name for momentum, which you call as impact, right? So it is not just the force over here. For example, another example I can cite here is nothing but you can take a marble. You can take a marble and then drop it from a certain height. Let us say from a 20-story building. Don't do this. Okay, many of us do stay in our multi-story building. Now you go to the 20th floor and from there you drop a marble. And then you drop a marble and you ask your friend to catch that. Or maybe, let us say there's a tiles over there. Okay, and if that marble comes and hits it, do you know what is the impact it creates? It will definitely break a tile. And you ask one of your friend to catch that marble, definitely it will break his bones. Okay, so this is what can happen because the size of the marble is so small. The mass of the marble is hardly 10 grams. 10 gram multiplied by 9.8 would be equal to 10 into 10 power minus 3 multiplied by 9.8. It would be very, very small. Okay, which would be hardly around 0.098 Newton, which is not equal to 1 Newton also. Okay, 1/10 of a Newton nearly. So that should not actually create any problem. But what creates a problem is that when it comes here, its velocity is so high. Okay, and calculate what is the velocity of this. Then you find out what is the momentum. And this momentum, okay, will come and hit the ground, and the contact for which the marble is in contact with the ground will be a very, very small duration of time. And as a result of it, the change in momentum divided by change in time will be larger, right? As the momentum is larger. So rate of change of momentum is larger, which means the force of impact is larger. The force, when we talk about it, it is not the force of the marble. When you just say the force of the marble, it is nothing but the gravitational force. But the force of impact is what one needs to calculate. So these examples definitely cite, okay, the importance of momentum while we start teaching this. So many students have this misconception. They always consider momentum to be taken like this itself. Okay, they just take momentum P equal to m into V and say nothing happened. Okay, they don't understand the concept of force. But anyway, these kinds of examples will definitely help them out to understand force. So there are many such simulations which are available in this. We'll look at one by one. Okay, now let us move on to the next one. Okay, let me go to the next one. So this graph, this shows you something like there is some Java lab. So a kid is now throwing an object which is throwing upward. Let me start this. Okay, so now she is throwing downwards, and as the object starts on coming downwards, so there's an adjustment given over here by the means of a slider, which is soft and hard. When you say it's a hard surface over here, okay, so what can happen is the ball bounces back, and you see the force which you have here is much larger, and the time of interval in which, okay, the object is in contact with the floor is also around 0.08 seconds or 0.09 seconds, not even 0.1 second. Now what I will do is I will now reduce this one to soft. Let me keep it over here. Okay, let me start this. Now let us see what happens to the force time graph and what is the impact of the force. Now what happens? The ball compressed to a larger one, and the force, as you see, the force is seen to be around 12 Newton over here, and the time of impact was seen to be much, much larger, right? And if I keep it at the center, what do you expect? Will it be 12 Newton? It will not be 12 Newton. It will be much more higher. Let us see that. Okay, it could be around 20 Newton. See, it's around 19 Newton, right? And the time of impact also has been reduced over here. Let me keep it over here. As the hardness of the surface keeps on increasing, the force which acts on the ball while it rebounds is also much higher, right? And as a result of it, so the force multiplied by time will also become larger. Okay, now let me move on to the next one. So this only shows you about, okay, how do you calculate the change in momentum and what happens to the force. And as you see, the force is increasing linearly, and then it comes to a plateau region, and once again it decreases as the ball leaves the surface. Okay, so this is what, okay, a typical force time graph can be seen whenever there is a collision being seen. Okay, let me go on to the next one. So this example is about having an egg and then changing the height, drop height, and also the landing surface, the type of the landing surface. Now let me start with the default ones. The egg size is small, drop height is 1 meter, and the landing size is a hard floor. Let me click on run trial. Okay, and let me drop the egg. What do you expect? The egg size is 40 grams, drop height is 1 meter, landing surface is hard floor. Definitely this will break, right? That's what you can expect. It comes here. it breaks across. You're not going to measure anything, you're just, that's what you're going to see here. The result is this much, and the force that acts onto it is going to be 44 Newton over here. Now what we'll do is let me change the conditions over here. So exercise is small, drop height is 1 meter once again, I'll get a foam box over here. Now what will happen? Just like a trampoline, right? When you drop the egg, this will not break, and as a result of it, you can see the egg is safe, and the force that acted on it is going to be 2.2 Newton. So why was this 2.0 Newton? The reason is because the change in velocity. See, the change in velocity is not what you compute from the drop point to the point where it is about to reach the surface. The change in velocity you need to calculate is from the point where it is about to reach the surface and the point when it comes to rest. Okay, that small thing, that is what you need to calculate. And the time interval is also that small time interval. If you calculate that one, then automatically F into delta T will give you change in momentum, and then you can divide that by the mass, you can get the velocity of it. Right? Like this, you can show several such conditions, and you can ask the students, okay, what happens? Okay, you can ask them to recoil. Let me go on to the next one. This is really a wonderful one. I like this very much. Many students, when I give this particular thing, they make a mistake. So this is a graph of momentum versus time, and there are buttons going over here like play, pause, and so on. And what we see here is that the initial velocity of it is 8 meter per second, and then the time at time t equal to 0, at x equal to 0, initial velocity is 8 meter per second. Now what we do is, let me play this. Before playing this, let me show you the controls over here. The applied force is going to be 10 Newton. Let me reduce this 10 Newton to somewhere over here. Minus 9. Minus 9 will not be helpful. Let me put a 2 Newton. Okay, or maybe I will put a 0 Newton over here. Put it 0 Newton. That means what? There is no external force acting on it. And therefore, what is the momentum on this? Momentum here would be mass multiplied by velocity. Let us first find out the initial condition. So, which should now be, when I click on this, you see the momentum is going to be 18 over here, 80 over here. When I say 80, since velocity is 8, so 80 divided by 8, it is momentum divided by velocity will give you mass. What is the mass then? 10 kg. So you had taken a 10 kg object given a velocity of 8 meter per second, thus the momentum is going to be 80. That's what we are seeing. Now what we'll do is, let us apply an extra force. Okay, let me reset this, and I will apply a force of 3 Newton over here. So as a result of it, now what will happen? Now this 3 Newton is now acting on the object for a time interval of 2 seconds. Now when I do this, see, this time is given, and after that there's no change, there's no force being applied. Only for 2 seconds the force of 3 Newton is applied. Let me click on this. So what do you observe? When it crosses the 2 Newton and 3 Newton itself, the momentum keeps on rising over here. So why does this rise? So what is exactly happening over here? So what is the initial momentum? 80. What is the final momentum? When you apply a force of 3 Newton for a time interval of 2 seconds, which means the momentum here is mass multiplied by velocity, which is 3 into 2, which is 6 over here. The total momentum now becomes 86. So therefore, from the fourth second, you observe the momentum, total momentum is going to be 86 Newton second. But why is it not increasing or decreasing? Because there is neither no friction or no any other applied force, no opposing force, no aiding force. So it remains the same, right? If I increase this, you can ask these kinds of questions to students. Okay, so if I put it to 6 Newton, let me reset this once again, 6 Newton over here, and click on play once again. So before we play, let us understand what is the final momentum. So initial momentum was 80, which we have seen already. The final momentum would be this 80 plus, we had 6 here, we have 2 here, 6 into 2 becomes 12. In fact, you can increase this also. Let me make it as a much larger over here. Let me make it as 5 itself. Okay, 6 into 5 becomes 30 seconds, 30 Newton second. So 30, and there it was 80, 80 plus 30 becomes 110. Now you should get the final plateau plot at 110 Newton second. Let us play this and see whether we get this as 110. And you should start after 5th second, or maybe second. See, why is it second? The amount of time the force is applied is again at t equal to 2 seconds. So therefore, after t equal to 2 seconds, it starts applying over here, right? Okay, so it's increasing. Next, so thus you can ask the student to plot different values of the momentum time plot, and then for different values of the force applied, how does the momentum time plot changes? Okay, this could also be a structured question in IB to do this. Okay, and because so far I have not seen such kinds of questions, they may ask in the future also. Okay, next. Now this is about a worksheet, okay, on linear momentum simulation. You can give this one as an FA to students, and they'll be solving this, and you can evaluate it to let them know, okay, how they have done this. Next one. This one is about impulse, and what you can see is there's an astronaut which is being so stuck in the space, and what he does is his mass is given over here, his extinguisher force is 150 Newton, okay, which means what? When I click on this activate button, so he has an extinguisher, he presses that one. As a result of it, the extinguishing agent, okay, is now sprayed outwards. So because of Newton's third law, he goes backwards. See, he goes backwards, and then maybe if I shut off this, now there's no force acting on him, still he moves over here. There are two photo gates over here, light gates. So as a result of it, what is the time taken by him to start moving from here to here will give you something like 11899 nanoseconds. And then what we can do is we can find out what is the distance between them, and we can find out the momentum, right? And we can also find out what is the force at which this was being, this extinguisher was being thrown out, or the gases have been let out. Okay, you can do this one also. You can change these values over here. Okay, so you can reset this once again. You can click on activate once again, and then maybe, okay, the moment it comes over here, I can now change this. Now you can ask the question, what did you understand from the reducing time? Okay, what is the hypothesis? We can put it across, right? As the person comes nearby to the photo gates, you see the time of crossing becomes lesser. So is it directly proportional? Is it indirectly proportional? What kind of relationship do we get it? Draw a plot, one problem, one simulation. You can actually create an IA using this. Okay, it can really help your students to do an IA based on it. Now let me move on to the next one. This one is once again a force time graph. Okay, now what we do is, let me click on this. So there's a force and time coordinates have been given over here. Let me click on the start over here. And the moment I click on the start, okay, wait, let me reset this. What's happening? The person is hitting the football. As a result of it, the football undergoes a deformation. And then once again, it leaves the contact and goes over here. So you get the maximum force to be equal to so much. And then you can find out what is the velocity. Velocity is seen to be 11.33 millimeter per second. What I do is, let me change the force of impact, time of impact. Time of impact is usually 0.042 seconds. So how do you get this value? We'll see this in a practical way. Okay, but wait for some time. Let me go for the tracker software to show you this of a Lionel Messi's football catching event. Now let me increase this time of event. Okay, that means if the feet is in contact with the football for a longer time, then there's a high possibility that the velocity will be larger. And that's what you need, right? If the speed of the ball is much higher, then definitely it is good enough that you can make it reach to a larger distance in a larger field. Let me click on this. So earlier it was somewhere over here. Now the time of impact, I have nearly kept it on 0.099 or 0.1 second. When I do this, what is the maximum speed it goes? The maximum speed it can go is around 26.71 meter per second. This is the maximum speed, right? Okay, now let me move on to the next one. Okay, this one, as you observe, this is only about a simulation from momentum and impulse, and this has some notes, and you can also conduct an experiment using an app known as Firefox, which you can download it in your mobile and then start working on this. There are apps like this which will help you out to do your experiment not only in the lab, but also you can do it using your mobiles. Okay, so maybe after this particular series has been done, so I would like to make a complete series on how to use Firefox. But anyway, Firefox videos are already available. You can just look into it, and you can start working on it. So really pretty good to work with this. Okay, all right. Let me move on to the next one. Wow, now comes our football player, Lionel Messi. So as you see here, there are two balls and he hits it over here. The interest is that, so this is in continuation with whatever we have seen here, right? So I have said that, okay, when the time of hitting, when the time of contact between the football and the player, okay, if it is much larger, then the velocity at which it hits becomes larger. Okay, but here let us understand what is the time at which he hits or how much time is he in contact. It's just to get to know about how to use tracker software. Okay, so now let me start with this. So this is what he does. I put the simulation at 0.25x. So he hits it, he catches it. Nothing great. Okay, so the regular one. Now what I will do is I would like to take up, I would like to start with this one. This is a tracker software. You can download it over here. Okay. Now let me click on this one here. Open a video, open file chooser. So I have the first one, Lionel Messi. Click on this. Now we have this here. The first thing that I will do here is that uh, I'll just calibrate it. I'll take this one here. There's a 1 here, right? I'll take up this. I will click on one of them. Click on new. Sorry. I click on new and click on calibration stick. So it's here. So first what I'll do is let me play this frame by frame. Okay, I can use my scroll button, or maybe I'll use this one here. So I'm moving this. As a result of it, I'll go to this frame. Oh. One more. Okay, I'll stop here. Oh, it's very precise over here. So I take this point as the origin, and then what I do is I'll still move maybe this as your final point. So I'll take this point over here. I take this point as the origin, and I will take this point as the final move. Or maybe I'll take this point as the final one. I want to analyze only for these frames. I'll make this as 1 meter. It's exactly vertical. Okay. Next, what I'll do is I'll go for the next one. See, I choose this one here. Next, I'll go for this one here. I'll click on the coordinate axis and choose this coordinate axis so that it is exactly at the center here. See, when I keep it to the center, I observe this is not exactly vertical. I'll align with this. Right. I align this. And after this, let me move back this slider back. It's almost the center. I'll keep it here. And then I'll go for the track. I'll click on new, click on point mass, and then I'll click his left feet. Now, before that, let me hold my shift button here and click on this left feet. And I've clicked over here. Shift, right, left click mouse. So enter key to clone previous. Okay, we have done this one here. So first point, as you can see here. Next point, what I will do is I'll move this slider a little bit. Put it a little bit farther away. Okay, let me click it over here. This is your second point. Then comes the third point. Then comes the somewhere over here, right? Fourth point. Fifth point. Okay, I've done 5 points over here. Now, as I kept on clicking over here, now you observe the time, distance, and y in meters. Everything is seen here. Now, if you look at this here, so which of them are here? So let us say, for example, so at which points were the ball in contact with the player's foot or the shoes? If you look at this, it was in contact at this point. It was this point. Where is this? This point. Which is that point? I can see it's highlighted. 6.04. And then it was in contact. It was in contact with this point also. 6.08. Which means the time interval in which Lionel Messi was in contact with the football, foot was in contact with the football, it seemed to be roughly around 0.04 seconds, right? Okay, so we already got it. We have not gone to the stadium, we have not gone anywhere, but we are able to find out, okay, where is he exactly in contact. Okay, so this, okay, so making use of this, we can find out with what force has I hit it on. If I know roughly what is mass, what is the velocity, I can do lots of research based on this. Okay, let me just come out of this. I'm not doing any research over here. I'm just showing you, okay, what all kinds of analysis one can do with this. Okay, now let me reshare my screen. Go back to this. Right. Let me go to the next one. Now, after getting this, I just want to get confirmed whether I'm doing it correctly or not. Okay, so what I did was I used ChatGPT. Many people say you don't use ChatGPT, but I use ChatGPT a lot, but use it in a reasonable way. Okay, don't just do it because you just got something. I think I had run this earlier also. Let me search in my, it's already here. And I'll show you this, what I did this here. So how long can one keep their feet in contact with the ball while hitting in a football game? Give me with references. I given asked this query and it searched over the web and it gave me some information regarding this. Okay, then there is nothing as such available. Then I changed my query and I asked it, what is the usual time I observed Lionel Messi? Uh, array. There is it. Okay. Okay, so this is what I observed. So I observed Lionel Messi through the tracker software, keeping the ball in contact with shoes for nearly 0.04 seconds. And then it looked into it and it actually gave me some references based on this. Okay, and it says, okay, there are some examples of which, okay, so these kinds of things are observed and gave me some articles. Now, I did not stop here. And then what I did was I looked at one of the articles. I took up one of them. For example, I took up this Tellis and Catis 2007, and I wanted to find whether such articles have been reported. So when I searched it across, I found out one such article which was not by Kirisan, this one, but a very similar article. Okay, do not trust ChatGPT every time. Okay, it gives you something, but you need to confirm, okay, how does it work? So as a result of it, I looked into it, and this is what I got. And here in one of the articles, he very clearly says that the time taken to hit is seen to be around 0.04 seconds. The velocity is seen to be 0.04 seconds. Okay, and it's in contact is so much over here. So in the research, the time spent between frames is 7 to 8 is 0.02 seconds, while between 8 and 9 is 0.04 seconds. So from there, he calculates the linear velocity and so on, and he has calculated the velocity of it. Okay, such kinds of things you can always do to conduct a research. You can ask the students to also use ChatGPT, arrive at meaningful conclusions, report what they have done, and finally, okay, arrive at research articles, get the data from it. Okay, and that's how ChatGPT would be very useful. Okay, and finally, arrive at what is that you want to do. Okay, so this is really a wonderful thing. I don't know whether one can really do some research or maybe an IA based on these kinds of things, maybe a literature survey, extensive literature survey, getting secondary data, analyzing it further, and so on. But this is already an analyzed data, so there's nothing much more for me to do it. But you can think, okay, creativity knows no bounds. You can always think about what best can be done. Next, let me go on to the next one. Newton's cradle. Every physics lab will have this. But unfortunately, we use this one to our children and say, okay, see, you just pull it across, it just goes here, hits and goes, it comes away. But this particular software shows me about how it is being useful. So it says, okay, there are 5 different balls over here, and then each of them, the masses of the balls can be adjusted. What is the potential energy, kinetic energy, and so on. Now, what I will do is, there's no friction, amount of energy, I can download the data. So in fact, I download data earlier. Let me redo this once again. Let me click on this run. Let me do this. Pull this for a certain height. Keep it for 1 joule. By adjusting this, what I'm doing is I'm adjusting the height and I'm keeping the potential energy to be around 1 joule. Okay, let me keep it here. Now what's happening over here? So this potential energy started dropping, kinetic energy started increasing. Okay, and then that also dropped it. There was a sharing between these two. And then after some time, see, between these two only the energies have been shared. But here there's nothing happening over here in between. So it's 0 joules. And all this were documented. And you see, data is getting downloaded over here. Okay. So you can get this value. You can download this value. You can get the value which is in the form of a CSV chart. And then you can go for an analysis. Then what you can do is maybe if let me stop this here. And let me change this value. Instead of 1 kg, I'll make it as 1.2 kg. This I will make it as 1.4 kg. This once again I'll make it as 1.2 kg. Okay, and let me run this. No, it doesn't run. See, something is smaller and so on. Let me take this, keep it to this much height. Again, 1 joule. Okay, now what's happening? Every object in it is having a chaotic motion. And you observe the energy is shared by all of them. If the masses were same, then it's a different story. If the masses were different, definitely each one of them is sharing it. And as a result of it, you can get data for each one of them, right? And then maybe you can plot it, you can comment on the conservation of momentum. You can do many things out of it. Okay. So these are some of the examples of what one can do with the online available simulation tools, how many different kinds of experiments one can conduct, and what is the inferences you can do. This is what I have seen so far. Okay, so you can also think about many such things, and if you get to know more about it, do let me know in the comment section, which will really be helpful for all the teachers. I would like to do more videos based on this, and see to it the entire physics learning community, not only IB, uh, gets benefited out of it, and we really do something good. In fact, because what I see is I had done many experiments. Basically, I am not a physicist. I'm a simulation man, as I told you people in the earlier video also. Um, I observe the students are not getting so much interested in physics, but I do a lot of things like this. But still, to make physics more interesting, okay, one has to not just watch simulations. When I go to other schools, view how students are working on it, I just see teachers, they perform experiments, they perform simulations. Okay, they just give it as an exercise. Students just pull something, leave it across. But what is that you infer? Nothing. Okay, that should not be. Of course, I don't say every teacher does it. Okay, but there are some teachers who does it. There are some students, many students. In fact, in my class also, many students who do this. So I don't want simulation to just be done like this, because people who create the simulations are great scientists. It's not so easy to create a simulation. In fact, with the vibe coding that we have, I tried to create something like this. It was very, very difficult. Okay, many times I tried recording and it was a mess. Okay, sometimes momentum is conserved, sometimes energy is not conserved. One or the other problem it has. But thankfully, many people have chosen to keep things free, and it is really helpful for most of us. Okay, so thank you everyone for being with me. Do like, share, and subscribe to my channel for more such updates. If you have anything to share, do let me know. Thank you.